and welcome to Dr. Logic Awkwardly Does Logic Home Office Edition. This is part one of what was to be the final seminar of the term for my third-year students in my formal and philosophical logic class at Durham University in March 2020, but due to the COVID virus, I'm doing it from the comfort of my own home. This was the week that we were supposed to get to finally proving Gödel's incompleteness theorem, what we have been working towards for pretty much the entire term. Unfortunately, it's a bit anticlimactic to have to do it over video. Nevertheless, I hope that we can get through the interesting bits and say a little bit more about the wider consequences of this result and talk about ways in which this result can be built on. Now, this class is primarily intended for the people who have been sitting in my seminars for the last couple of months, but as with my other lectures, anybody is welcome to listen in. If you have any questions or comments, please leave them in the comments. I will try to get back to you. If you've got if you would like recommendations for further reading, let me know. I can give those to you. But I am going to give a little bit of a recap because we've gone through a lot of material in order to get to the place where we are. And it's also been a couple weeks since we've talked about any of it, so I want to make sure everybody's on the same page with the same background and information. So, this is our teaching assistant, Goldwine. He will hopefully be helpful rather than unhelpful. Anyway, now that he's no longer blocking the board, this is the roadmap that we started with a couple of months ago. The idea that we are taking is statements about piano arithmetic can actually be converted into statements about numbers, and therefore we can express them in the language of piano arithmetic and not just make statements in English about them. So we developed the coding system. We associated individual numbers for each of the primitive symbols of piano arithmetic, and then we gave methods for turning those symbols into codes for terms, for variables, for atomic formulas, and so on and so forth. So we started off by defining properties that will hold of numbers that are codes of certain types of formulas or variables or whatever. So for instance, we defined this property var, which is going to be true of any number that is the code of a variable. We also defined the property 0, which is going to be true of any number which is a code for 0. Now, if you go back and recall back to the encoding system that we defined, the code for 0 was 2. Therefore, this property that we defined is going to be true of all and only the numbers that are identical with 2, because 2 is the only thing that is a code for 0. Once we have codes for variables and 0, so 0 is our only constant in our language, we can then define when something is the code of an atomic term, because it is either a code for 0 or it is a code for a variable. Then we have codes of sequences of terms that are put together in a particular way that allow us to kind of build up more and more complex terms. So we can talk about when a particular sequence yields a term, so that term occurs in a sequence of a particular type. We can talk about when a particular term is yielded by or obtained from a particular operation, for instance, the successor operation, or addition or multiplication. Then we can say when we have a code of a sequence of numbers, each of which encodes a particular type of term in a particular order, and these are the term building sequences that we introduced at the beginning of the term. Different term, the academic term, not the logical term. And then we have a general way of stating whether something is the code for a term, whether it's atomic or complex. This bit of the roadmap covers terms, but then we do exactly the same thing again when it comes to looking at codes for formulas. So we only have one type of atomic formula in piano arithmetic, and those are equations, so identities of individual terms. So these are going to be either variables or 0, or things that can be built from variables, 0, and the arithmetic functions. So whereas here we've got var and 0, here we just have equations. So we are able to characterize all of the numbers which are Gödel numbers of equations of terms. Those are then going to be our atomic formulas. We can also obtain formulas through negation, conjunction, and universal quantification. So this feeds into the build formula property in the same way that all of that fed into build's term. Then we can say when we have formulas. So if I give you a number, you can then check this definition and determine whether or not that number is the Gödel number of a formula or not. There are two types of formulas that we are interested in when it comes to encoding derivations or proofs in general. We want to have axioms and we want to have implications, or more precisely, we want to know when is one formula the consequence of some implication for which we already have the antecedent. So just as we have kind of the atomic side and the complex side for building up terms, and then we have the atomic side and the complex side for building up formulas, we have the same sort of structure when we look at proofs. We can think of proofs as being building sequences that follow certain rules, where our atoms are the axioms. So we have either first order logic axioms or piano arithmetic axioms. These make up all of our axioms. Or we have something that has been derived from an axiom given one of the given some implication and the presence of the antecedent of that implication. So that is what we have over here with the implies. We plug these together, then we can say when something is a derivation is a sequence of formulas of a certain type. But since we're putting this all into the language of arithmetic, something will be a derivation if it codes a sequence of numbers, each of those numbers is itself a code for a particular formula, either an axiom or an implication. Then, at the very top, and I know this is somewhat harder to see, but this says theorem. A theorem is the result of a derivation. So something is the code of a theorem if you can find one of these derivation sequences and that number occurs in the sequence somewhere and encodes some sort of formula. Because if you have a derivation, every single entry in the derivation is going to be a theorem of the language. So now we are at a point where we can talk about things that are provable in PA and things that are not. And this is where we have been heading for the last couple of months. The overall idea, just to remind you, is that we want to come up with the statement of some sentence which is true in... Oh dear, I've just lost the focus. Let's see if we can get it back. Nope, we are going to have to pause this video here and come up, and I'm going to have to reset things and start again. See you in a bit. Welcome back to Dr. Logic Awkwardly Does Logic, part 2 of the Piano Arithmetic Gödel's Incompleteness Theorem lecture. I have figured out how to fix the autofocus. I have changed the brightness and the contrast. Let us hope that we now have something that will work and be legible. Anyway, when we finished up the previous video, I had just gotten to the point where I was saying what we want to be able to do now that we can express this concept of what it means for some number to be the code of a theorem in piano arithmetic is we want to be able to pick out a sentence which is true in the natural numbers, but which is not provable in PA. So if we can get a sentence like this, then this is sufficient to show that piano arithmetic is incomplete with respect to the standard model because there are true sentences that cannot be proven. Now, this notion of provable, we need to kind of convert this back into the language definitions that we've been talking about so far, namely that this notion of not being a theorem. So we want to be able to say of something that it is a true statement and is not a theorem. The method by which we will construct this sentence is the method of what is called diagonalization. And I will define some of the relevant properties first and then say something about why it is called that. It has to do with a very nifty little kind of physical representation of formulas and their codes. But I'm going to start off by giving you a definition. So this definition is the diagonal of a given formula. So if phi is a well-formed formula with one free variable, x, so we could write it phi of x, then d phi, the diagonalization of phi, is defined as follows. So d of phi is phi, and then take the code for the formula, so this formula with one free variable, and substitute it in for the free variable x. So there is a sort of self-reference that's going on here by taking a formula, figuring out what its Gödel number is, and then substituting that number in for the free variable. So the idea of why this is called a diagonalization has to do with this sort of thing. Take all of the formulas, all of the well-formed formulas in piano arithmetic, and just put them in order. So say we've got, actually, all the formulas with one free variable. So you've got phi 1, phi 2, phi 3, phi 4, etc. Now, we can take substitution instances of each of these. So first, you could say, well, phi 1 with 1 substituted in for it, phi 2 with 2 substituted in for it, and so on and so forth. Now, you could do it this way. The other way that you could also do it is, say, take each of these numbers, each of these formulas corresponds with a Gödel number. So we've got the Gödel number of phi 1, the Gödel number of phi 2, and so on. And then we can take this number and replace it for each one of these free variables. So whatever number this happens to be, substitute it in for the free variable, and what you will see is that, so phi 2 in for x, the ones where the code for the formula gets substituted into the formula itself are all along this diagonal. So that's where the idea of this being called a diagonalization comes from. So I'm going to start keeping a list of important definitions up at the top. Hopefully we will continue to have enough room, but this one we will definitely keep because it's super important. So the diagonalization of a formula that has one free variable is the result of taking the code for the formula and substituting it in for that variable. Before we can move on to the next set of definitions that we need to be able to define the Gödel sentence itself, we need to be able to say when one thing is the Gödel number of something else. So, in particular, we need to be able to have a way of translating the concept of being a Gödel number or being the code for something into the language itself. That is, what we would like to have next is a well-formed formula that has two free variables, so phi x, y, which is true, so that this is going to be true of a pair of numbers n, m, if and only if n, the code of n, is m. So we're looking at codes of numbers. These are themselves numbers, so we can put together identities like this. So, for instance, whatever formula this phi is going to end up being, it will be the case that it is true of the pair 2, 0, because 2 is identical to the Gödel code for 0, because as we defined in our original encoding, the code for 0 just is 2. So we would like to be able to do this for all numbers. We know what the 0 case is, so now we need to say when is something a successor, and when can we find this identity between numbers and their codes. So that is our next goal. We're going to define what it is to be a successor sequence. So a successor sequence is going to be anything that just is a sequence of natural numbers starting at 0 and going up to some point without missing any numbers out in between. So successor sequences will be sequences like the sequence containing 0, the sequence that has, these are successor sequences, 0 has no business in them. It's any sequence starting with 1, going up to some natural number without any gaps in between. So the sequence containing just 1 is a successor sequence. Sequence containing 1 and 2 is a successor sequence. 1, 2, 3, 4, 5, etc., because we never need to count much further than 5. All of these are successor sequences, and we can pick out a property that is going to be true of all of the codes of these sequences. So, you know what a successor sequence is. I'm going to erase that because board space is at a premium. We've got our next definition. I will write it up here right away so that we've got it underneath our definition of diagonalization. So, definition, we will have this property successec for successor sequence. Some number c is the code of a successor sequence if the following is the case. So first, it has to be the code of a sequence, and we know that the value of the first entry in the sequence has to be 1 because they all start with 1. So entry C1 is going to be the code for successor of 0. And then what we want to be able to say is that for any two adjacent sequences, the next one is always, the value of the next entry is always going to be the successor of the value in the previous entry. So what we get is that for every n, for every e, and for every e prime, if we have that the value of the nth entry of the sequence C is e, and the value of the sequence after that, so the successor of n, is e prime, some more parentheses in there, then we know that e prime needs to be the code of the successor of the value that is encoded by the value of e, which is to say that e prime is 2 to the code for successor times 3 to the e. So parenthesis, I think we just need that one. So something's a successor sequence if it is a sequence, the first entry is 1, And for any pair of adjacent entries, so the nth entry and the successor nth entry, are always going to be offset from each other by the by each value being the successor of the previous value. That's just what it is to be a successor sequence. This then allows us to identify when something is the Gödel code of a number. So Gödel codes themselves are numbers, but you can also give codes to numbers. And since Gödel codes are numbers, you can give codes to those numbers, and you can give codes to codes, and you can give codes to codes to codes. And before you know it, there you are, sitting in your bedroom, isolated because of COVID, and you have just coded all numbers with other numbers and more numbers and more numbers. And at that point, you should probably go outside and take a bit of a walk. But we have this definition of number. Now, it's really super important at this point to remember that we are not trying to remember what a number is. We are trying to identify things that are codes for numbers. These codes are also numbers, but we are looking at when is one thing a code for something else. So, this is why this property number is a two-place relation that holds between two things, n and m. So we can read this as n, which is a number, is coded by m, which is also a number. When is this the case? The definition is that first, there is one of these successor sequences. So there is some code or some number which is a code for a successor sequence. And the value of the nth entry in the sequence is m, because the first entry is coded by its value, the second entry is coded by its value, the third entry is coded by its value, and so this is how we get this correlation between numbers and their codes. So something is a number if either there is one of these successor sequences and an appropriate entry within it, or, because we can't forget 0, n is 0 and m is the code for 0. So, every number is either 0 or a successor. This is something that we would have proven some weeks back if we hadn't been on strike. But then we can turn this into an actual property that's expressed in terms of other numbers by saying, well, either n is 0 and it is coded by its code, or we have something that codes a successor sequence that has the appropriate entry in it. How are we doing for time? This brings us to our first half an hour, so we will pause and take a break, and I will get back to you.